my computer crashed and all the work that I was doing in the previous video has died and disappeared. So I've lost all that. We did get to basically this point where we put in every stage of our energy level diagram, okay? We hadn't got to the point of putting in the values yet. Now, I'm not going to go through each and every value. I just want to make sure you know what the values should be. Okay, so in your textbook, you were given values for all these different enthalpy changes. This first one here, as you can see, aluminium here is going from a solid to a gas, and you've got 2 moles of that going on. So effectively, this enthalpy change is 2 times the enthalpy change of atomization of aluminium, which had a value of plus 326. So you should plonk in plus 326 there. And that would have to be multiplied by 2. So in other words, your enthalpy change there is plus 326 multiplied by 2. Okay. Now let's just take another random arrow. Let's take this one. Now, obviously, this is going to be a negative value because arrow pointing down means exothermic. So let's talk about what's going on there. Well, we're going from here, where I've got the eraser here, to here, okay? So effectively, we're going from gaseous oxygen atoms, okay, to gaseous oxygen ions. So effectively, you've got 3 times the enthalpy change of, the electron affinity of, or the first electron affinity of oxygen for this change here. So they've given you that value, so it would be 3 times, this is representing for this arrow here, just in case it's a little unclear. So that would be 3 times the first electron affinity of oxygen, which is 3 times minus 141, okay? So hopefully you know what each of these arrows represent in terms of the value you have to put to that arrow, okay? Now, when it comes to the calculation, you don't have to do it in one way. I believe that in my last example, we looked at it like this. We said, well, this value here, we could say that that is root 1, let's say. That would be the same as going all the way around like this to get to there, okay? So in other words, that's root 1, that's root 2. And if we were writing that equation out, we'd write delta H lat, because that's 1, that would effectively be 1. Okay, root 1, let me erase that mess there, equals, where's my pen? Equals the sum of root 2, okay, so sum of root 2. Now, if you're doing that way, you've got to be careful with your reversing of the signs if it's necessary, okay? Because if you're going against an arrow, effectively you're doing the opposite enthalpy change, okay? So you need to make sure that any positives become negatives and any negatives become positives, okay? And of course, you need to make sure you've got the correct molar quantities. So that would be one way to look at it. I do want to talk about the other way of looking at it, though, because you might find it easier that way, because that's how they're describing it in the textbook. Remember, this is all about Hess's law, so basically, independent of the route taken, you're still going to get the same result. Let's get rid of these 2 values. In the textbook, I believe it says that it looks at it like this. It looks at going from here to here, which is, of course, your delta H formation. Let me just erase that. Would be the same as going from here to here, all the way around like that. Just kind of thinking it as the opposite way as the first option I gave you, okay? And again, this is possible due to Hess's law. Now, if you were to do it that way, then the equation you form is going to be slightly different, because you're saying that this being root 1, let's say, and this being root 2, this arrow being root 2, you're saying that the delta H of formation equals the sum of root 2. I'm just going to put R2 for root 2. But remember, you don't know this value, because this line right here, if I have to overlay an arrow here, let's just do it in red. This line right here is representing your lattice energy isn't it? Okay, which is actually what you're trying to find out in this calculation. So we can call that x because we don't have a value for that. So when we think of it this way, then we're saying the delta H of formation equals the sum of root 2 plus x. In other words, x is part of that sum. And all you'd have to do then is to rearrange that equation in order to make x the subject of your equation. Okay, you can do it at the end or you can do it at the start. It doesn't really matter. Now that's the way that a lot of tutorials will be showing you how to do it, and you might be more comfortable doing it that way because it might be easier to understand, but it's entirely up to you. The point is there's different ways you can look at the calculation or the final calculation, because you can be thinking of applying Hess's law in a slightly different way. Okay, so we had two ways to do it. I'll just quickly recap on those. One way is looking at it like this, where you could say that, well, this value here would be the same as going this way, like that. And the other way that I just showed you was that we could say, well, this value here would be the same as going whoop, like that. Now, either way you do it, you should get the same result. And I was pretty happy to see that the answers that were posted online on the classroom were the same as what I got, which was, let's have a quick look. I think you guys, yeah, so you guys are the two people who posted answers, both got the same answer as me, which was -14780. So well done indeed. I did actually check the answer book and they've got a different value, but I went through their calculations and I think that the answer they've done is actually incorrect. So well done, guys. Okay, good luck. Bye-bye.